Okay, good. And there are a few participants. All right.
What time?
All right, well, there's not much left of this class. Here we are. Today, Project 2122. (12/6) is the last class. And the final exam, 12/13. No, 12/30 is the last class. Okay. And 12/30 is the final. Okay. All right, the final will be online like your other quizzes in this class, and we'll see how that works.
That's the 20th.
12/20. Thank you. A little better. But I'll probably have it available for a whole week, but you only get one chance at it. All right. Anyway. All right. And the scores are up. And the scoring system is here. And the people in green already have an A. So they do not need to take the final or do anything else, although you're free to if you like. So, are there any questions about anything? Well, let's finish up with the crypto. There's a little more of the crypto chapter to do. And then I think I just want to show you an attack from the cryptology class that I thought was fun. I put it in as extra credit in this class. There's an awful lot of extra credit projects in this class, but I think they're good for you to do. All right. So down here, here's the public key infrastructure. We talked about the mathematical part of cryptography, but then there's the networking part of cryptography, which is not math and which often introduces the weaknesses. So there has to be some way to move these keys around. And that's the public key infrastructure. So this is a bunch of servers and protocols and computers trading data around to try to make it secure. Now, the whole problem with the internet, of course, is the internet's only issue was availability. When it was in its early design phases, and many parts of it were never upgraded for anything else. So it is a self-healing network that is very likely to move data from one place to another, and all cryptography has to be added to it at a later level, all other kinds of security besides availability. So you have to have somebody to know who you're talking to. So that's done with a certificate. This is the standard, the X509 certificate, that's got the name of the company and then the name of the organization that issued the certificate, and then some mathematical numbers here to try to guarantee that this certificate is authentic. So the public key is the most important part here. The public key is the long cryptographic number, which you can use to encrypt data, and nobody can read it except the owner of the certificate. And you have a third party vouching to say you know who it is, so you have this third party thought is trusted, and they tell you that this is really Google. And if you encrypt stuff with this key, nobody can read it except Google. That is the system. And this is basically an American product, so it's based on trusting rich people. That's how our system works. So you have these certificate authorities that are companies that live entirely by selling these certificates and verifying them. And if the idea is if they were not honest about that, they would go out of business. So they hopefully have a financial incentive to protect their network and not lie. Unfortunately, that system is the invisible hand of Adam Smith from 250 years ago, and it turns out to have a failure when people form conspiracies, which is what Thomas Jefferson saw. He said, you know, this system we designed in America is only going to work for about 200 years, and then it's going to collapse because people will be corrupt and form conspiracies and overthrow all these protections. And we will see. But anyway, what happened here is there's an awful lot of ways for people to make even more money by lying. And it reminds me of what I've read from anthropologists to try to figure out Humans are not monogamous, but what they have adopted is the most common sexual arrangement is monogamy plus cheating. And both the male and the female have a reason to cheat and lie about it, and they will benefit from that if they don't get caught. And this is the same thing here. And it's turned out the certificate authorities have been doing a lot of rotten things and not getting caught for a while, and making more money in the short run by doing rotten things that will come out. The main one being, if you are rich enough, they will sell you a root certificate so you can sign things, and then in the middle traffic, and customers can't receive it. And this is so common that there's a bunch of law enforcement espionage gear that just has a USB port where they say feed in the public certificate here, and companies buy it and they use it at the gateways out. So when you do an HTTPS connection from inside a corporation, your browser does not give you a warning message, but you're actually not making an HTTPS connection to the end user in many cases. And it's the problem. You have to trust people, and no better system has emerged. But this system does simply rely on trusting all these companies implicitly, and that's a problem. Anyway, so you buy these certificates, you only get to use them for a certain period of time before they expire, and you have to pay for the renewal. Although now the Electronic Frontier Foundation has been messing with the economic model. These things used to cost hundreds of thousands of dollars a year, but now the EFF has been giving them away for free. And Let's Encrypt, their free site, is now been around for more than a year, staying up and very popular, as you would imagine, giving out free certificates. So anyway, you can renew your certificate and keep using it, or you can get a new one. But if you lose the private key, or you otherwise feel like the security of your certificate is compromised, then the issuer has to put it on some list saying it's revoked. And in theory, people who browse to a site using a revoked certificate will get an error message. Now, unfortunately, studies have shown that the vast majority of users completely ignore certificate error messages. And by the way, they are correct to do so. This is where I think Microsoft really shines. Microsoft decided to really study the social engineering aspects of browser usage because they're trying to make Internet Explorer safer. And they said there are some people that worry about the technical details of the code, but they said, let's look at the user experience. They said the main problem with users is they click on a link and they go to a fake site that pretends to be a bank or PayPal, and then they give them confidential data. Almost no criminals use HTTPS for those fake sites at all because the user doesn't know what HTTPS means. Modern browsers don't even put a padlock or anything, so you can't tell if it's HTTPS or not. So they just make an HTTP site, which will load faster and look pretty good. So when you see a certificate error, in practice, it always means it's a genuine site with a problem like they've got to renew their certificate. It's very unlikely that it's an HTTPS site because it's much more productive for the criminal to just make an HTTP site. Although now, so many sites are HTTPS, criminal sites are beginning to be HTTPS also. But anyway, that's why the error message for certificates is universally ignored, and probably correctly so. And this is something little kids and users are good at. They know when their parents are telling you don't do something, but it's really okay to do it anyway. Then they just do it anyway and hide that fact from their parents. And users are this way about things too. And certainly, all of my family members who have Windows machines are completely desensitized. Every time they turn it on, many boxes pop up full of gibberish they cannot understand, and they've just learned to close all that junk and keep going. And so another box full of meaningless gibberish accomplishes nothing. And Microsoft knows this, so when Microsoft Internet Explorer goes to a known phishing site, the whole screen turns red. It says, don't go here, this is a bad site. And they hide the button to continue in the corner where you can't find it. They said this actually has the result that 99% of users will not go to that site anymore. And so they're right about that. They're trying to communicate effectively to the end users. Anyway, so certificate revocation list is the original system to keep track of this. And the crazy thing about it is each certificate authority, of which there are more than 100, runs their own list, and they run their own servers. And in the certificate, it tells you where to go ask about it. And those servers aren't really efficient. It takes too long to get an answer from those servers. So almost every browser has a fail open policy where it will ask the CRL, wait something like 50 or 100 milliseconds, then just give up and let you through to the site if it doesn't answer. And they usually don't answer in time. So in fact, it's a shame. The revocation system is so inefficient, it doesn't actually stop you from going to those sites, with the exception of Chrome. Google figured this out, and they made a non-standard way of handling this, which is all the revoked certificates that aren't already expired is a short list. So they just put it in Chrome directly. It doesn't have to ask anybody. And with the Chrome update, it comes update to that list. It has a local copy of all the bad certificates, and it knows they're there. No other browser does that as far as I know. Anyway, there's another field that has come and perhaps gone. I think I've read some people say they deployed this and then they took it back. This is where you have to get into threat modeling. A mathematician would like to make the system perfect so nobody can get in, but even they have to define what the attack is. And real companies have to really think about, what are you worried about? So here's what you're probably worried about. You connect to Google, and it's really Google for a long time. Then you go to a coffee house where somebody is actually doing art poisoning and man-in-the-middle-y thing, and suddenly it's not Google, it's signed by some fake thing. That's what the realistic threat probably is. Therefore, that's what STS is for. You put this header in your HTTP page, and it says, remember who signed this certificate. And if it changes to somebody else, they're more unusual. So this is pretty much like what SSL has. SSH does not have certificate authorities. Instead, the first time you connect to a server, it prints out the fingerprint saying the fingerprint of this server is here. Is it okay? You say yes, and then if you connect later and the fingerprint is different, then it gives you an error message. It tells you this, somebody appears to be lying to you about what the server is. So that's the plan here, and it sounds pretty good. And you can put it up here. You'll see it down here. Here's Facebook has this strict transport security right here. So the first time you go to Facebook, your browser will remember who signed it. And if you go to Facebook later and somebody else signed it, your browser will warn you. This doesn't look like a genuine Facebook. You appear to be in a man-in-the-middle attack. That's the plan. So that might be good. I've heard some people say this turns out to be too much difficulty in the long run, and people turn it off. All these systems have the problem of key handling at your end and at the other end, and that turns out to be a huge problem. So that PGP, for example, the most secure encryption system of all, where everything you send is encrypted with public key encryption, with RSA, which can be very long and essentially unbreakable. This is what Snowden used to leak secrets from the NSA. And it's, as far as anybody knows, it's perfect and unbreakable, but the key handling problem is so enormous that even the developers that invented it have quit using it and publicly said, I gave up on it, it's useless, because you have to have this key everywhere you go. And invariably, you don't. You're at home, you're at a different system, unless you just have copies of the key everywhere where it can get stolen, you're going to end up not having the key when you need it. It's very annoying. Anyway, so you have to back up your keys. Like now, the current system that is really in use, HTTPS, also has private keys. Now, the users don't have private keys they have to handle. What happens is your browser generates a key pair every time you connect and then throws it away when you're done connecting. Uses it only temporarily, which is fine for the client. But the server is Google. They paid for a certificate. They have thousands of people all using, probably millions of people all using the same public key. They have to have that private key. So that means if their disk crashes, they can't be losing the private key. So they have to back it up. So now you have to make extra copies of something secret and store them off-site. And that's an issue. I imagine they're probably encrypting their backups by now. When I was talking to companies years ago about this, I couldn't convince them to encrypt their backups. But your backups are all your confidential data. If you lose those, you're going to have a really bad day. But a lot of companies have the habit of just throwing backup tapes around like nothing, because most of the time you never use them. So they regard it as a low priority. So you just take some minor employee and say, oh, take this home with you or something. And then it gets stolen out of the car. That's happened. And now you've got a data breach. Anyway, so the security authority has to back up their private keys, and they have to have some way to, they'll also back up keys for their customers and recover them if necessary. So the certificate authorities are visible in your browser. There's just a long list. You see here somebody called Baltimore and many others. The government of China is in there and many other certificate companies. And this is put in by the people that made your browser in their wisdom. There is no inspection process. There are no written rules for how secure you have to be a certificate authority. There are no rules of what you have to do to maintain this. It is just what whatever browser manufacturers do. And every now and then there's a scandal and somebody gets hacked, and then some browser manufacturers choose to take them out of the list. And if enough people do that, they go out of business. That's how it works. So it's really, that's the way a lot of the internet is. Border Gateway Protocol is the same. There are 2 million administrators that can dump out BGP packets. And if they do it wrong, they snarl up traffic on the internet for as many people as they like, because there is no system in place to limit whose traffic you can affect. But if you do it enough, people get mad at you and just put you on a blacklist and block you. It's informal and regulated only as sort of an old boy network, sort of a club of people make decisions about it. So you can make your own certificate authority. The certificate authority server is really not doing anything more complicated than what your browser does to make the other end of the encrypted tunnel. You just have to generate public and private keys and hand them out. You can install certificate services in Windows or any other operating system. You can choose what encryption routine to use. This was an old version of Windows. The only choice they had here was SHA-1. Browsers won't accept SHA-1 signed certificates anymore because SHA-1 now has collisions since February of this year. So everybody had to upgrade to SHA-2 in a hurry, or the users will get error messages. But this old version didn't have it. You choose your systems, and then you can hand out things. So you can have your own certificate authority, but nobody's browser will trust it. Now, this is what companies are supposed to do. If you want to man-in-the-middle HTTPS, you make your own CA, and then you push out the identification of that CA to your company employees who add it to their browser. And now their browser won't complain when they connect to sites and you're man-in-the-middle them. But if they bring in their home laptop that doesn't have that extra key added, then they will get an error message. That's what you're supposed to do. What they really do in practice is what I say. They bribe certificate authorities to give them a root certificate. And that's one of those open secrets like China hacking everybody that everybody knew but nobody would talk about until about 2-3 years ago when TrustWave publicly announced that they had been accepting bribes to hand out root certificates and they had now quit doing that. And there was a huge storm, and Mozilla in particular said we should take them out of Firefox because they're bombs. And they said, no, you've got to listen more carefully. Everybody in your current list is still doing it. We're the only ones quit doing it, which is, of course, a statement we cannot verify, and they probably don't really know, but it is common practice. And you know that because there's hardware you can buy that comes out from the Spooks and Suits conference, which is, I don't know how this conference can exist. It's a public conference with public security officers and espionage officials meeting to talk about techniques. And then they have public talks and reveal. One of the many things they have is a shopping list of what the spies buy. And it's amazing this stuff becomes public, but that's where it became public. There's all these commercial boxes to buy where you just plug in a root CA and it intercepts everything. And so obviously those things are not that hard to obtain in reality, although they're not supposed to be obtainable according to the trust model. So there are cryptographic attacks. The simplest one is, of course, look for plain text. So this is chapter 1 of every cryptography book. If you're trying to break cryptography, first look and see, is it really encrypted at all? An awful lot of things are supposed to be encrypted and they're actually not encrypted. So just sniff the data and you might be able to read it. You can, even if you see that it's encrypted, you might be able to just replay it without decrypting it and get into somebody's account or something. So that works sometimes. Active attacks will now try to determine the key by sending specialized traffic to it. The one thing a lot of manufacturers love to do is to not tell you what cryptography they're using. Almost all the experts agree that this is a terrible thing, and if the company you're using will not tell you what cryptography is, then don't use them, because it's almost always something awful. Naively, people would think it would be more secure to keep our algorithm secret. But in practice, it's not, because there are a lot of stupid or poorly applied algorithms out there. I find all the time on Android. So what most people find is better is to use a public algorithm that everybody knows about, that is known to be good, and all the secrecy is in the key. That's what usually works. However, the military keeps their algorithm secret and their key secret. So they just keep everything secret. That's their security model. So the birthday attack is important for cryptographic hashes. If you ask everybody in the room what your birthday is, just month and day, and if you have 23 students in the class, the odds are that 2 people will have the same birthday, which is counterintuitive, because you have to carefully consider the question you've asked. If I asked a different question, does somebody here have the birthday of January 1? Then it would take 183 people before we find somebody with January 1, because there's only one chance in 365 that each one of you have that, and we'd have to have about half of 365 people before we'd have a 50% chance of finding a specific date I chose. But if I just want to find a coincidence of 2 dates out there, then I could match you, I could match him, he could match him. So the question is not how many people there are, but how many pairs of people there are. And the number of pairs of people is the number of people times the number of people minus 1 over 2, because each person can match someone else, but they can't match themselves. So there's n minus 1 people to match. And if you're going to compare 2 people, it works the other way. So you double count if you count them all. So that's the game here. And you'll find that if you have 23 people, 23 times 22 over 2 is large enough that you have a chance, more than 50% chance that 2 of them have the same birthday. So in practice, that's a stunt, a parlor trick, but it shows a mathematical issue which affects hash functions. So if you're hashing something and you make a hash function like an MD5 that's or SHA-1, which is 160 bits, then you naively might imagine that you have to calculate 2 to the 160 hashes before you'll find one you want. And if you wanted to find a hash of a specific type, like they were all zeros, that's what you'd have to do. But if you just want to find 2 files that hash to the same value, then you would have to try 2 to the 80 collisions. Now, 2 to the 80 calculation is more than anybody can do. The largest brute in 1997, there was a brute force attack to crack DES that tried 2 to the 56 passwords. So that's achievable. And the brute force attack of 2 to the 64 has also been done. A brute force attack of 2 to the 72 is in progress and expected to take 1,000 years, which might sound stupid, but if Moore's law continues, 1,000 years is really only 20 or 30 years before computers get 1,000 times faster, and that'll amount to that time passing. But 2 to the 80 is out of sight. There is nobody anywhere that has tried 2 to the 80 of anything. And there's a pretty good argument that it never will. So this SHA function should have been fine, but it wasn't. It got cracked because it had mathematical defects that made it possible to try less than 2 to the 80. There were some patterns people were able to find in it to take some of that complexity away. Anyway, so that's the birthday attack. Even if it was a perfect hash collision, you would only have to do 2 to the 80 calculations to find a collision. And once you've found 2 files that hash to the same value, then a variety of disturbing attacks become possible, because now a SHA-1 signature is not really a unique signature. Anyway, so there's kind of mathematical attacks. There's ciphertext only attack. This is the worst. Where if you can fall for this one, you've got a terrible system. Like WEP. WEP has this problem. Why do you go from Firesheep? You just sniff the traffic and do nothing else, and go until you got a few million packets. You could just do math on those packets and figure out the key. And that is terrible. That's essentially unusable at this point. You're wasting your time in a system like that. There's a known plain text attack, which is another one that works even faster on web. This is, if you're going to be encrypting something like network traffic, then you've got a problem, because network traffic is in fact very easy to guess. Most network traffic is ARP packets. The ARP packets are easy to spot because they're smaller than all the other packets. And almost every bit in an ARP packet is totally predictable and repetitive. So you actually know what it is. So you know the plain text, you observe the ciphertext, and that's, of course, making it easier to deduce things about the key. And then there's chosen plain text, which is what we're going to play with later with the padding oracle attack. This breaks a whole lot of systems, where if I am actually allowed to submit data to the server, and it will encrypt it and let me see the encrypted results, and I can carefully choose malicious data to feed in, then often I can find special data to feed in that will give me information I'm not supposed to have, like information about the key. Like you might intuitively imagine that encrypting something that's all zeros, then encrypting something with only one bit that's 1, might easily tell you something about the key, because most of the calculation will all be zeros. It turns out to be a little tougher than that, but not a whole lot tougher than that, and we'll do it later. The chosen ciphertext is another way where you can see the ciphertext and the resulting plain text from track decryption routines. Anyway, a brute force attack is what you're hoping. A brute force attack is the attack that will always succeed if you try every possible key. That's what happened to DES. The key was only 56 bits long, and they tried all of them, 2 to the 56 of them. There's nothing that can stop that attack, really. This is the best you can hope for, is if there is no mathematical shortcut, then they have to try every possible key, and then the only question is, how long is your key? And of course, if it was 1975, 2 to the 56 was impossible to achieve, and therefore it was okay to use DES. But by the 90s, it was no longer okay, because 2 to the 56 was now within reach. So that's the issue. You could try brute force your passwords, every possible character, but the problem is after you get above 4 or 5 or 6 characters, it turns out to be way too many combinations, so even the fastest computer can't try them all. And that's why brute force attacks are easily defeated by just making the key long enough. Now, a man-in-the-middle attack is the active attack. This one is really dangerous, and this breaks almost all protocols, HTTPS being the only common one that resists this. You get in the middle somehow, so the victim thinks they're talking to the server, but they're really talking to you. So you think you're talking to Google. I'll pretend to be Google. I give you a key, you encrypt your stuff. I can decrypt it, then I re-encrypt it. Google thinks I'm the client, and you think I'm Google. This is actually devastating. It breaks almost all cryptographic protocols. You have to think about this. So now if you have HTTPS, there's a third-party certificate authority, and I can't fool them. So I will hand out a fake Google key, but when your browser asks the certificate authority, is this really Google's key, they will say no. And because they've used a public key encryption scheme, they have numbers they can verify in that certificate that I can't forge. That's the way it works. So unless I'm able to steal or bribe a legitimate root key out of the certificate authority, you will get a warning message if I man in the middle of your attack, your stuff this way in HTTPS, and that's the idea. However, there are a lot of nasty tricks. One nice effective one is a downgrade attack. An awful lot of people can pick your servers and then they don't touch them for a long time. So if you have let your server sit there for like 15 or 20 years, then it was using really old protocols. So I can tell them, I'm sorry, I'm Windows 95. Internet Explorer 3, I can only handle 40-bit keys. You'll have to downgrade the encryption to that level. And if your server has not removed the old stuff because you just haven't updated it in a long time, then it will cheerfully negotiate down to that level. And now I'm using encryption that's easy to break. So this tends to happen. And one particular huge problem is export data encryption. The United States government had a very unwise policy of outlawing the export of strong encryption from the United States as a military secret until about 1997. And so Microsoft, Windows, and many other products, in order to comply with federal law, had a special weak encryption in the versions of the operating system that were sent overseas. They called it an N at the end or a K at the end for the versions that we'd sell in foreign countries, and they had weak encryption that was trivial to crack, 40 bits. So many servers wished to be visible on those implementations of Windows. So they had to have the weak keys on the server to talk to the export versions of Microsoft products and other products, which was all complying with federal law. But the result was it's like creating a population of vulnerable machines, like people that are unvaccinated for smallpox or something. We've now created a population of machines that cannot talk strong cryptography. And they're out there, and people are using them, and businesses want their website to load on those machines, so all the servers have to accept downgrading to these unsafe cryptographic schemes. And therefore, you create problems for decades in the future with this kind of unwise policy decision. Anyway, in reality, almost nobody does brute force attacks against passwords anymore because most people, their passwords now have to be 6 or 7 or 8 characters long, and it's pretty impossible to do brute force attacks out that long. I've heard some people talk about 10 characters, but that's pretty extreme to have a machine that can do that. What they do is they use a dictionary of stolen passwords, and those have come out. The biggest one was the RockU list. There are a few billion stolen passwords out there publicly available. So you try them, that's a very small number. A billion's not much at all to try, and you usually get in accounts that way because almost everybody's password, somebody has used that password before, often the same person. That's why individually, people ask me, like, what can I tell their relatives when I go home for Christmas to make them more secure? And as far as I can tell, the best thing you can tell them is to quit reusing passwords. That is probably the most dangerous thing that normal people do. They have 1 or 2 passwords, use the same password everywhere, and this is really bad because people get hacked all the time and leak their passwords. So either show them how to use a password manager like LastPass, or tell them to just write it down on paper and put it where you put your $100 bills. That would be all right too. Or put it in your address book at home. Keep it somewhere where you won't lose it, but have a different password for every site. That alone would make you a lot safer. Anyway, so there's programs like John and Cain and Abel and many other programs that will crack passwords. Then there's replay attacks, like the Microsoft hash the hash attack is here, and the one you did in the projects where you replay a cookie. Often you can take a number that is sent to the web from somebody else's session and just replay it from your browser and get in their session. Now, all they would have to do is add an anti-CSRF token to the web page, which would be something unique to that viewer. Like you could connect it to that IP address and add the IP address to something and hash it and make that the cookie. And then if somebody from a different computer tried to play that cookie, it wouldn't be accepted. There are a lot of tricks like that you could use, but a lot of websites just don't. So you can steal a cookie and replay it from another network and still get in. And of course, there's a reason for that, beyond just laziness, which is portable devices like cell phones. I can log into Facebook on my cell phone and get a cookie and then move to a different network and get a different IP address. And Facebook doesn't want to make me log in again. So they accept the cookie from a new IP address now. And that's, mobile devices really almost never ask you to log in again. And that means once somebody steals a cookie, it's pretty much theirs forever. And even resetting your password in most systems does not make the old cookie stop working. I did that a few years ago and showed that at DEF CON and everything. So it's That's why it's a good idea now that Google blazed the trail that more and more sites are actually going to 100% HTTPS, which means all your traffic is encrypted all the time, and I probably can't steal your cookie because the usability of the system pretty much relies on persistent cookies that are reusable from multiple locations. And so Firesheep was one of the many products that was used at security conferences to dramatize this problem. This is, you'd imagine, because the people experts in the business, once you demonstrate something awful, they'll scramble and fix it, but it's not that way at all. Once you demonstrate something awful, next week some celebrity just go on the system for another 7 years. It's over and over and over again. You have to have people with the same thing before they finally notice. Firesheep was one of them. You just boot this up, it would snip the network, find passwords for social media sites, and just put them there. You can just click on these and get on other people's sites. This had like 1 million downloads in the first couple of days it came out. Everybody could just go to coffee houses and get it everybody else's accounts. At this time, it worked for everything. Google, Facebook. So most of these big sites then made minor upgrades to break this particular tool. And then in a few years later, they actually went to HTTPS all the time, which would prevent this. So this is not as bad as it used to be, although it's still plenty bad. All right, so password cracking. If somebody dumps a bunch of hashes on the internet, you can crack them. I've done this plenty of times. I've done it with U.S. military passwords that were dumped out. I was teaching a class and I was up all night cracking U.S. military dump. I mean, the next day, here's top secret passwords right here, and real credit cards. That was in the days of WellSec. Technically, that's illegal, which I didn't know at the time. But you can certainly crack your own password. Anyway, you have to get the password file somehow. Hackers usually get them by SQL injection and dump them publicly. But if you want to get them off machine, they're in X password or X shadow file. X shadow file is where they are on modern versions of Linux. And they're in the SAM database on Windows. And you get these hashes, and then you can crack them with a variety of tools. They'll all just try a lot of guesses to crack it. Now, there's a few other entertaining ones. The one you just did in one of these late project 21 or 22 is SSL strip. This is Moxie Marlinspike, and it was very brilliant. All you do is man in the middle of the traffic and then downgrade it from HTTPS to HTTP. And people will look perfectly fine, especially on a portable device, and people will not know that it's not encrypted. And the server won't know that you're not encrypted because the man in the middle is communicating server HTTPS. This was extremely effective for about 10 years before browsers finally started upgrading to fix it. Again, typically, Chrome upgraded first. Starting about a year or two ago, Chrome just put a list of which sites should be secure, and they've memorized in the browser the top 1,000 websites and whether they should be secure or not. So if you try to go to Facebook over HTTP, Chrome will not let you. Say, no, that should be a secure site. Other browsers aren't that smart. But now, and I think I had upgraded the project and showed you a while ago, the modern browsers will now warn you. If you type a password into a site or a credit card number that's not HTTPS, they will say, this is not right. Which is even better. That will encourage the sites that still have plain text login to knock it off, and there's plenty of them. Although now it's getting down to like 1% of college login pages anyway, which is what I've investigated that are plain text. Anyway, this is one I mentioned before, which is pretty awesome. You can make a wildcard certificate that will sign all the pages at a website like star.samtrash.info. But you could also buy this one, star, and then nullbyte.evil.com. And that will be interpreted as valid by the certificate authority because their code is written in Pascal, and a null byte can be stuck in a string harmlessly there. But your browser that was written in C will interpret the null byte as terminating a string. So it will interpret this as star, which is a wildcard. So it will accept this for every domain. And there were about 19 of these certificates sold to security researchers before they went public with this and people found out about them. Supposedly they've all been revoked now. And supposedly all these certificate authorities have upgraded their system so they won't sell certificates like this anymore. But it's a huge problem because it was not exactly a bug in anyone's software. The Pascal code was running as intended and the C code was running as intended. It was the conversion from one language to another that caused the problem. And this happens over and over and over. And if you take I think we're doing a web application hackers handbook class next semester. And this this is the main thing that happens on websites because a typical server is running something like 8 or 10 different languages, and so is your browser. So there's many spots where something created in one environment is interpreted in a different environment, and it often leads to security problems. All right, then there's renegotiation vulnerability. You can, for some reason, renegotiate a session and demand a new key, and that turned out to weaken the system. Like I said, they often fail to trust certificate revocation lists, and your browser trusts highly untrustworthy people like the government of China to sign websites. So it is kind of nuts, the current system, and various people like Moxie, Marlin, Spike have proposed other systems where you have some more complicated trust structure than just trusting everybody in a list, but none of those have become popular yet. So I got a few cahoots about this stuff, and then I want to show you the padding oracle attack, which I've added to your projects as an extra credit project.
I have a question on extra credit projects.
Yeah.
Can we do as many as we can to get credit, or is there a max limit?
There's no limit on the extra credit projects. That's a very good question. So you can do them until the last day of class. You can even do them until the final, but then they'll be late. And you can do as many as you want, so it is pretty easy to get enough points to get a day without taking the final. And I think that's fine. Just don't copy somebody else's images. That would be a problem. But if you're actually doing them, I'm perfectly happy. If you want to do more hands-on and less terms out of the book, that's fine with me. Yeah.
How much is the final?
About 80 points. So it's really not that hard to achieve. If you look at the scores here, the final is 70. And the projects are like, 10 or 15 or 20. So 3 or 4 projects could easily be as many points as the final. And as you see, there's people here with over 700 points. And the total I thought was only like, the total required stuff is only 650. So it's quite achievable to do a bunch of these projects and get enough for an A without taking the final, and that's the way most people prefer to go. But if you do want to focus on the information in the book and that sort of thing, then you can do it the other way by taking the final. Or you can just take the final because you like to be complete about things. Some of these people may choose to take it even if they've got an A without it, which is fine.
Is the final, sorry, I'm a little late. Is the final in person or?
I'm going to put it online like the quizzes this time. So that's new for me. I used to make people come in and do it on paper, but I'm not seeing much reason for that, especially since a lot of people don't even take it. I'll try it this semester, putting it online like the quizzes. I'll try to make it so that you can't just look up the questions easily in the book. I got to work on writing a final that's intended to be open book, but I'll give it a try that way. Good. These are good questions. Whoops, and that's the wrong one.
I have to charger.
Yes, I do.
Thank you.
Yeah, that's all you need, right?
Yes, we'll do
Good. Yes. If you don't have a working phone, the Kahoots become much less entertaining. All right. All right, there's the number. We've got some paper to write down winners on. Kahoots. All right. 6. There may be more. Yeah, it looks like we're at 7 online and about 7 or 8 in the room. There may be some more. I'll wait another 10 seconds. All right. There may be only 7 Cahooters. Another Kahooter. Okay. Oh, here they're still coming. Okay. I'm certainly glad I didn't keep that guy out. He might get really mad. That guy tends to fly off the handle.
I'm not that sweet.
All right. Let's give it a shot. 4 questions. All right. So who issues the certificates? Okay, the certificate authority, that's what they're for. Okay, where do certificates go when they are bad?
I don't know.
Okay, we go to the certificate revocation list. All right, what attack will always work if you have enough time? All right, brute force, good, okay. What attack is made easier by export grade encryption? All right, it was the downgrade attack because there was this weak thing to downgrade to that everyone had to put in their products. Otherwise, it would have only been the worst people that don't update their stuff that would have been vulnerable. Daniel Callahan and two people. They're going to have to tell me who they are, Kaji and YJZ. Aha, YJZ looks like initials. And so it is. Okay, I found out who YJZ is. And Kaji, is Kaji in the room? Kaji's online. Well, Kaji, I see your name. Okay, good. Okay, so I have identified the people. Good. So what I'm going to do, you've been almost an hour. I'm going to take a 10-minute break. At 7, I'm going to start the Zoom session again. I'm going to show you the padding oracle attack from the cryptography class, which I added to this class. And I wanted to make it a separate video so because people might well want to look at one and not the other. So I'll be back in 10 minutes, or right at 7, I guess 8 minutes. Stop this one.